Hassler here. I'm going to give you some notes on 3.6. We're going to be looking at higher derivatives. And all that means is that we are going to take the derivative repeatedly over and over and over again. So we're repeatedly differentiating a function. That means that if f of x is differentiable, if I'm able to take a derivative, then the second derivative would be the derivative of the first derivative. Okay? It's given as f double prime. So there are two little primes here. Or I'm taking the derivative of the first derivative. Okay? The second derivative is the rate of change of f prime. So it's the slope of the f prime graph. Notation would be f double prime with those two little, looks like a quote almost. Or in that Leibniz notation, it would be d squared y, take the second derivative of y with respect to x, dx squared. So the third derivative in that notation would be dy, or d cubed y over dx cubed, okay? So I'm going to go through and do a few of these with you. If the notation is given with the primes, I just use the prime. And if the notation is given in Leibniz with the dy dx, I use that notation. So let's take a look. I have to calculate the indicated derivative. So this means that I have to find the third derivative of this function. So I'm going to start off by saying, all right, well, the first derivative is 15x to the fourth minus 4x minus 14x to the negative 3. Right, power rule, multiply coefficient by exponent, subtract 1 from the exponent. So I'm going to take the derivative of that. So this would be the second derivative. When I take the derivative of that, I have 60x cubed minus 4 plus 14 times 3, which is 42, x to the negative 4. And then I'm going to take the derivative of that, and that would be my third derivative, f triple prime. And so now I'm going to do 60 times 3, which is 180, x squared. The derivative of my constant is 0. And then negative 4 times 42 is negative 168, x to the negative 5. And I'm going to leave it like that since I was given a negative exponent, and this would be my final answer. All right, so not so bad. Not so bad until you get to fun things like roots and trig functions. So again, we're going to find f triple prime, the third derivative. And so remember that this is the same as 4x to the 1/2. The 4 is not included with that x to the 1/2. So just to be clear, again, first derivative. When I take that first derivative, I get 2x to the negative 1/2. But I'm not going to worry about putting this back into root form because I have to take the derivative again. And if I put this back into root form of 2 over the square root of x, I would have to convert it back to this form in order to take that next derivative. So don't work harder than you need to. All right, second derivative would be negative x to the negative 3/2. And then my third derivative, f triple prime, is going to be positive 3/2 x to the negative 5/2. And then because this was given in root form to start, I'll put this back in root form. I get 3 divided by 2, the square root of x to the 5th. All right, let's keep going. Oops, sorry. Here we go. All right, so now I'm going to have you calculate the second derivative. That's so kind of me. We'll stick with our theme here. And so I have tangent of 3x. Got a little chain rule happening in here. So I got my first derivative, f prime. Derivative of the inside is 3, and the derivative of tangent is secant squared. Whatever was inside stays there. And then I have my second derivative. Now, what's interesting about this second derivative is I have two chain rules happening, right? This really says 3 times the secant of 3x, that whole function squared. So if you need to do that rewrite to help, then do it. All right, so derivative of the outside would be 6 x to the first, but whatever was inside stays inside. So secant of 3x. I'm running out of space. I'm going to say dot times. Then the derivative of the inside middle layer, which would be secant, and the derivative of secant is secant tangent, but I need that 3x in there instead of just x. So secant 3x tangent 3x times the derivative of the innermost function, which is 3. So if I clean this up a little bit, I've got 6 times 3, which is 18. I have 2 secants being multiplied, so I can say that that is secant squared of 3x. And then I have my tangent of 3x. And that's how that goes. Great, next problem. All right, this is that Leibniz notation. It says calculate d squared y for dx squared. Find the second derivative. Oof, product rule. All right, so my first notation is going to say dy dx is equal to, and I've got my product rule. Remember, this is the first derivative. So product rule says derivative of the first times the second plus derivative of the second. Love the e function. Derivative of e is e times the first. And that's fun. Now, there are a couple of things I could do from this point on. My answer key does the product rule twice. So my answer key says, okay, well, I have a product rule here to do, and then I have a product rule here to do, and I'm going to add those results together. Could do that. I could factor out things that they have in common. And so I could say, well, and I could just do it as an e to the x if I wanted. They have this e to the x in common. So I could factor that out and then do one product rule. That sounds like fun. I could do that. And so there's a couple of different options that you have here. I'm actually going to go back and do the product rule twice just so I can get a little extra practice. But you have choices here. All right, so I'll do red so that I don't run into whatever happened here. So I have d squared y over dx squared. So I have to do this product rule twice, right? Derivative of the first times the second plus the derivative of the second times the first. Here, I'll do this next one in a different color. So we've got plus product rule here. So derivative of the first times the second plus derivative of the second times the first. And then the only thing I can do to clean it up, I'll do that part in green, is combine any like terms. And it looks to me like I have, did I miss something in here? 2x, 2. I did something wrong on my answer key. That's a bummer. It looks like the only thing that I have here that I could put together is this e to the x 2x and this 2x e to the x. Since the x terms are the same, there's no exponent on there. I get 4x e to the x. And then I have these leftover terms, right? So I have this plus 2e to the x plus this, I'm going to resituate these, x squared e to the x. All right, so I got to fix that. All right, still hanging in there with me, okay? Hope so. All right, let's do problem 5. And oh, yikes. All right, I see on problem 5 that I have some implicit differentiation that's going to happen here. So I need to find the first derivative and then the second derivative. The problem is that I got y's sprinkled throughout. So that tells me I'm going to have a little implicit differentiation. So let's do dy dx. So the derivative of sine is cosine of y stays there, times, remember when I take the derivative of a variable that is not the independent variable, I have to multiply by the derivative of y, so multiply by y prime or by dy dx equals, you know what? This is my fault. I never should have said dy dx equals because I didn't start with the y equals. Shame, Hassler. All right. Equals the derivative of x, which is 1, plus the derivative of y, which is dy dx. That's my bad. I should not have started with a dy dx because I did not have y equals. I should start right with the function that's given. All right, my job is to isolate this dy dx because I have to take the second derivative. And the thought is, well, I have two dy dx's. What do I take the second derivative of? Well, really both. But I'm going to go ahead and I'm going to isolate this dy dx. If I do that, I would subtract. So I would have cosine y times dy dx minus my dy dx, which is equal to 1. And so dy dx is equal to, if I factor that out, I'm going to have 1 divided by cosine of y minus 1. This is actually going to be really important here in a little bit. So I'm going to box this off. I'm actually going to box this off in red. That's how important this is. Okay. Now I'm going to come and I'm going to do the second derivative. So I'm going to take the derivative of this. I'm going to take the derivative of dy dx. And the derivative of dy dx is d squared y over dx squared. I can start out here because that's what's on this side. I should not have started with dy dx equals because there was no y here equals. There's no y equals here. It started with sign. So that was my mistake earlier. I'm allowed to do what I'm about to do here because I'm starting with dy dx only. And the derivative of y with respect to x of dy dx is d squared y over dx squared equals, gross. If I take the derivative of this to me looks like I would have to do a quotient rule. And I absolutely am allowed to do a quotient rule, and I don't want to do a quotient rule. Okay, so what I can actually do is I can actually rewrite this, and I'm allowed to rewrite this to say all of this is raised to the first power, so I can move all of this to the numerator as long as it's being hugged by parentheses and raised to the negative first. Yes. All right, you with me? All right, let's see. I'm going to run out of room, so I'm going to have to erase this. Because I'm not going to have enough room to do what I want to do. So I'm going to leave that this dy dx is equal to, I know if I don't get rid of these little things, somebody's going to be mad. All right, so I'm going to leave that dy dx is equal to, and I'm going to leave it as cosine y minus 1 to the negative first, because I do not want to do the quotient rule, but you're welcome to. And if you do the quotient rule, we should end up in the same spot. So now I'm going to do the derivative, the second derivative, so the derivative of dy dx, which is d squared y over dx squared, is equal to, now I can do my power rule, right? I've got negative 1 times that quantity cosine y minus 1 to the negative 2 times the derivative of the inside. Derivative of the inside would be the derivative of cosine. So that's negative sine of y. But I'm taking the derivative with respect to x. So I got to say times dy dx. And the derivative of negative 1 is 0. So I don't need that. Fun. Okay. So, that's a real bummer because this has a dy dx in it. And that's okay because I know what dy dx is. Dy dx is cosine y minus 1 to the negative 1. And so when we solve these problems, these implicit differentiation problems, and I'm asked to find the second derivative, you should end up with something like what I have here, where there's a dy dx in that second derivative. And that's okay. I'm going to replace. So negative times negative is a positive. I can actually make this whole thing positive. And I'm going to replace this dy dx, so sine of y, with cosine y minus 1 to the negative 1. This should say negative 2. And I can clean this up a little bit, right? I still have my sine of y that's being, raised to a positive exponent. I can bring this down. and I can bring this down, or I can multiply them ahead of time. If I multiply them ahead of time, this becomes cosine y minus 1 to the negative 3. So when I bring this down here, I've got cosine y minus 1 to the positive 3. And that is all equal to the second derivative with respect to x. Okay, so implicit differentiation, I'm going to take the derivative like I've done before. I'm going to isolate dy dx. When I take the derivative again, I'm going to end up with this dy dx. I'm going to replace it with what I found in the first round and then simplify if I can. All right, my friends, if you have any further questions, please ask. See you soon.